31 is another very good question. So we have two spheres, both on insulating stands. They're saying, what are the charges on X and on Y after the rod is placed in contact with them, as they've shown? So initially, it says X is uncharged and Y is positively charged. So this is positive, and this one, X, is negative. Oh, sorry, neutral. Now, given the fact that Y is positive, what does that mean? It's going to induce a negative charge, is going to bring about, actually this is charging by contact, induction is when they're not touching, but it's going to be negative. Now, if the rod is negative, what does that tell you about X? That it will give X the opposite charge. So eventually, both of those will actually be positive. So 32, this is a generic question. It says, which row describes the charge on an electron? We know it's negative. And what's the direction of electron flow? It's negative to positive. So it's Y to X. Now, again, don't do it directly. What you need to do is just draw something like that. That's it. Why are we drawing it? So that you can explicitly see that electrons are flowing from Y to X, and you don't mix it with X to Y. Second thing, if they had asked you about conventional flow, we know that's from positive to negative. That would go like this. In that case, the answer would have been X to Y. It doesn't matter which one you're considering, but just to remind you, in the O-level syllabus, IGCSE, we're always dealing with conventional flow. So we always say it goes from positive to negative. In reality, what's happening is that electrons are going from negative to positive, but it does not make any difference which way you're thinking of it. What you need to know is technically electron flow negative to positive and conventional positive to negative. Okay, so another question where I'm going to show you why that method works so well. So let's say I don't read the question. Obviously, don't do that on the exam. You have to read the question. But the point is that if I just look at the details, I'm going to say this is Q, because that's what I use in the syllabus. This is T. This is E. All right, now let's see. Charge passes through a resistor in 1 second. Then in 2 seconds, 20 joules of thermal energy is produced in the resistor. What's the potential difference across the resistor? Now, let's just assume that I'm the student and I'm having trouble solving this question. Just because of these symbols, you hopefully should be able to work your way through the problem. Why? Because I know that using Q and T, I can calculate I. So let me do that. I is Q over T, 0.4 over 1. The current is 0.4 amps. Now I see, okay, I know E. Then for that case, I again know T. And I also have I available. What do I want to calculate? V. So then I ask myself, okay, using E, I, and T, can I calculate V? And if you can just do that, the equation will jump out at you. You know, it's V is equal to EIT, the product of that. So 20 times 0.4, and the time is 2. So 20 times 0.8. Oh, I hope you realized E is equal to VIT. So the energy is equal to the product of V, I, and T. That's what I was wondering, why is the number not working out? When you rearrange V, you get E over IT. E is 20, I is 0.4, and T is 2. So 20 divided by 0.8, that's 25. So the answer is 25. So again, that's the point I was trying to make. Use the paper to your advantage. Whenever you get a numerical question, read the question, and then the very first thing you do, just put the symbols of all the quantities that are mentioned in the question. And you can put it to the test. Do it tonight or tomorrow, and you'll see it makes the problem far easier because the equation just becomes obvious. All right, 34, which meter measures the current in resistor R2? We know that ammeters always go in series with the components. So it's going to be D. That is going to measure the current in this branch. If they had asked you which one is going to calculate the total current, it could be A or C because they're both correct. I'm just telling you that those ammeters are calculating the total current. Why are they calculating the total current? If you want to visualize a circuit, you can do this. Let's look at conventional flow. Goes to the left, goes down, then goes right. As soon as it hits the first junction, it splits into I1 and I2. Then it travels like this, and from both branches, they reach this junction, and that's where they recombine. After that, you once again have the total current leaving that junction. So you see it reconnects and then splits, and that keeps happening cycle after cycle. Okay, similar question. Charge of 1.5 flows for 0.003 seconds through the flash lamp. Average voltage is 3600 volts. What's the electrical energy supplied to the flash lamp, and what's the average power? Again, let's put that method to the test again. This is Q, this is T, and this is V. What are they asking us for? E and P. We know that E and P are both related. We can go with either one. Now, using Q and T, what can I calculate? It's I. Then, using V and I, what can you calculate? Should be obvious, it's power. So let's do that. I is Q over T, 0.003. So how much is that? 1, 2, that's 100 times 5. So that's 500 amps. And then P is going to be V times I. Voltage is 3600 into 500. Now, there's an easy way to do it without the calculator, but obviously you can use the calculator. So 3.6 into 10 power 3 times 5 into 10 power 2. 3.6 times 5 is 18. So 18 into 10 to the power 5, but standard notation will give you this. 1.8 into 10 power 6. Why? Because the first number needs to be less than 10 in standard form. So that's the power. If you want energy, you can simply multiply it with the amount of time. But in this case, we're already done with the question because there is no other choice that gives you this as the power. So you see, it's a very effective way and a very quick way of solving numerical questions. And the best thing about it is that it'll come to your rescue even if you're having trouble conceptually as to why the calculation looks like this. Which lamp lights when S1 is closed and S2 is open? Again, a very good candidate to demonstrate the fact that you need to use the paper. How do you use the paper in this case? You draw this on the paper so that you can visually see the actual circuit that you would get. Now, what does that tell us? That you have this as a complete circuit. So the current is going to flow end to end. Whatever components you have along the circuit will light up. So L1 and L2 would light up. L3 is not yet part of a complete circuit, so it does not light up. 37, which statement explains why the hairdryer does not need an earth wire? Now, I'll just quickly tell you that what's the concept of an earth wire? It's to prevent electrocution. And why are we worried about that? Because if the live wire, the one that's carrying current to the appliance, is, let's say, malfunctioning, and it touches the metal casing, in this, what you call it, hair dryers don't typically have metal casing for that reason. But when you do have metal casing and the live wire touches the metal casing, what's going to happen? The casing will become live. It will become charged. And when you touch the casing, it's going to electrocute you. The earth wire neutralizes that charge, the buildup of charge. So it is basically a mechanism. It's a way to protect people from getting electrocuted. Now, why would we not need an earth wire? Well, we would not need an earth wire when we have some other kind of substitute for protecting people from getting electrocuted. And what is that substitute? It is double insulation. So that even if the first layer gets compromised, let's say the live wire is touching the first layer, then you have a second layer behind it, which is safe from the charge. In other words, you do not get electrocuted. So actually, that is why C is correct. 38 is a simple demonstration of Fleming's left-hand rule. So we know how that works is that first one, again, if I were you, I would not pick choices directly. I'd first do this force, let's say magnetic field, and this one shows current. And now I would just pick the choice. Why? Because you have to understand that test taking is a separate skill. So you may be very good at physics, you may be very good with the concepts, but you may not be a very effective test taker. So those are different things. That's why use the paper to your advantage. Don't think or don't do problems in your head when you don't need to. So put everything out there and then think about it consciously. 39, you move a magnet through the coil. They're saying which change must increase the size of the reading. Okay, so what's the background? The background is that as soon as you move this through the coil like that, what's happening is that you are cutting through the coil, each loop of the coil. Every time you do that, this magnet basically has a magnetic field, right? Now, let me move it again so you can visually see it. There you go. We've just cut the first one. And then as we keep moving, we cut through additional coils. Whenever we cut, what happens? The rate of change of the magnetic flux basically changes. So whenever the magnetic flux changes, it induces EMF, which then induces current. In other words, the rate of change of magnetic flux is what indicates the induced EMF or the induced current. If the rate is very high, you will induce more current. So they want the size of the reading to increase. What does that mean? They want a larger induced current. What's the way to produce it? You need to make some kind of change that basically increases the rate of change of flux. So what's that? We can push it in faster. That will increase the rate at which the coil is being cut, and that will increase the rate of change of flux. That'll give you a higher current. Now again, you see, the logical reasoning aspect is just very explicit. It's not something I'm doing. It's something that's inherently part of physics. Electrical power is transmitted by cables over long distances at very high voltages. What are the effects of using a high voltage transmission system? So what's going on here is that over long distances, we want to maximize the voltage. Why do we want to do that? Because a higher voltage requires a lower current. Now, if it requires a lower current, what's the benefit of that? Well, you're going to have less heat produced. If you have less heat produced, what's the benefit? You'll have lower losses. So you're losing less amount of energy as thermal energy. And that's why we do it. So the power loss at high voltages is going to be low. The current is also going to be low. And in fact, the power loss is low because the current is low. And what's the logic? If you start from here and you go to another place, if you ignore power losses for a minute, what's the input power? It's V times I. What's the output power? It's also V times I. Generally, what is P? Simply V multiplied with I. What that means is that any power, let's say the power is 1,000 watts. You can transmit a power of 1,000 watts in many different ways. For example, case number 1, you use 100 V as the voltage, 10 amp as the current. You use 500 volts as the voltage and 2 amps as the current. You have many such combinations where the product is going to be 1,000. But which one's the best? The one with the highest voltage and the lowest current. Why? Because the power loss is going to be minimized.